Good morning, students. If you can see the screen and you can hear me, just one of you just message me that you can see the screen clearly. Okay, I think I'll start now. So in last class, we have started thermodynamics. We have talked about what is thermodynamic system, what is thermodynamics variable, how many types of thermodynamic systems are there, and what is the indicator diagram. So these basic things, I have introduced these things. We have done the basic definition of these things. Now we are going to, and then we, in the last class, we have considered the as I told you that thermodynamics is the study of heat, energy, and work interconversion. So then we have started with the internal energy of the gas. We have written internal energy of the gas can be written as F by 2 nRT. This we have derived this thing in the chapter called as kinetic theory of gases. From this, I can write change in internal energy of a gas is going to be F by 2 nR delta T, because number of moles of the gas are not going to change. R is a constant. So temperature is going to change. So I can say internal energy of an ideal gas is only depends on the temperature. So internal energy is function of temperature only. It does not depend on the pressure or volume. If you change the pressure but temperature remains constant, internal energy will be constant, or change in internal energy will be zero. Then from this, I have told you this thing also, what is F by 2. From the formula, gamma is equals to 1 plus 2 by F. I can write F by 2 as 1 upon gamma minus 1. So from this, we have written other formula of delta U also. Delta U can be written as N R delta T upon gamma minus 1. Now this term F by 2R is also written as CV. So I can write this thing as NCV delta T. Later we are going to derive this thing. Then NR delta T can always be written as P final V final minus P final, P initial V initial. So I can write this thing as P2 V2 minus P1 V1 divided by gamma minus 1. So this is the formula, different formulas of internal energy or change in the internal energy of the gas when temperature is changed. So remember, if temperature is not changing, we can say internal energy of the gas will remain constant. So at temperature constant, internal energy remains constant. Change in internal energy is zero. Different formula. This is in terms of degree of freedom. This is in terms of atomicity of the gas. This is in the molar specific heat capacity at constant volume. And this is in the terms of pressure and volume. Now, we have to use the sign convention for delta U. So I think I have to start from here. Now, for sign convention for delta U, as you can see, delta U is U final minus U initial. So if U final is greater than U initial, which means internal energy is increasing. If internal energy is increasing, then I take delta U as positive. Sorry, delta U is positive. Now, when this thing is going to happen, when the final potential, sorry, final internal energy is going to be more than initial energy, when the temperature in final is more than temperature initial. So from here, I can say if temperature increases, then also delta U is positive. So if in a thermodynamic process, temperature of the gas is increasing, then we say delta U is positive. Internal energy change in the gas is positive, which means final internal energy will be more than initial energy. So this is the sign convention when internal energy is increasing. What if final internal energy is less than internal energy? This will means that internal energy is decreasing. If internal energy is decreasing, what will be delta U? Delta U is negative. When this thing will happen, if final temperature is less than initial temperature, which I can say temperature decreases, then also I can write this thing. So if internal energy of the gas is increasing, we take the sign convention to be positive. And if internal energy of the gas is decreasing, then we take the sign convention to be negative. This another way I can say, if the temperature of a gas is increasing, change in internal energy is going to be positive. And if temperature of a gas is decreasing, then change in internal energy is going to be negative. So this is the sign convention and formulas for delta U. Next thing we have to study is heat exchange. So suppose you have a container. This container is closed with a piston. This is the piston. And in this container, there is gas. Now, what I can do is, if these walls of the containers are conducting, if walls of the containers are conducting, then it is possible that the heat can be exchanged. So heat can be exchanged with the surrounding. If a gas can exchange the heat from the surrounding, there are two possibilities. One possibility is then you can give the heat to the gas. Another possibility is, see, you have a container. This is the piston. Another possibility is you can take out the heat from the gas. So basically what the gas can do, if these walls of the walls of the container are conducting, the gas can absorb the heat from the surrounding. It is called as heat absorb. And here you can say heat released. Release, or you can use the word ejected, or you can say the rejected. Any of the word is fine by the gas. Remember here gas is our thermodynamic system, so I can call it as heat absorbed by the system also. So don't get worried about when you hear the word system or no. Gas and system are same in thermodynamics. Most of the question gas and system are similar only. So if gas, you give heat to the gas, then we call it as gas has absorbed the heat. And if gas is releasing the heat or gas is throwing the heat out, then we call it as gas is released by the. We have studied a chapter called as heat transfer. In heat transfer, we have seen that the heat exchange, to increase the temperature of the body, heat exchange can be written as NC delta T. Where NQ is the heat exchange, this is heat exchange. And for gases, we don't use the mass, we use the molar number of moles. So this is the number of moles. And here this is called as specific heat, sorry, molar specific heat capacity. And this thing is called as change in temperature. So this thing we have studied in the heat transfer. So here also the same thing is valid. So if a gas is exchanging a q amount of heat, if gas is absorbing the heat or releasing the heat, I can write the amount of heat absorbed or released by the gas. I can write it as NC delta T, where C is the molar specific heat capacity. And for a gas, there are different molar heat capacities depending on what is the thermodynamic process. So for gas, we can have different type of molar specific heat capacity. Two are important. One is called as Cp, another is called as Cv. What is Cp? Cp is molar specific heat capacity at constant pressure. And second one is Cv, which is molar specific heat capacity at constant volume. Other also you can define molar specific heat capacity as constant temperature, molar specific heat capacity in adiabatic process. For different process we are going to see. But remember, this is general specific heat capacity for any process. For us, two will be important, which will be Cp and another one will be Cv. So this is the formula of heat exchange we are going to use. Later, we will derive another formula also from the first law of thermodynamics, which we'll see slowly. So this is the thing with the heat. Now again, for heat also, we have to use the sign convention. So for sign convention for heat exchange, if heat is absorbed by the system, we sometimes call it as Q in. In means the heat is going inside the system. So if Q is in or heat is going inside the system, then we take Q as positive. Obviously, you can think of this thing, and if you want to relate it, you can relate it by the your bank balance. If you put money inside your bank account, then you get the positive sign. If you take out the money from your bank account, you write the minus sign. So same thing is for the heat. And if heat is released or rejected by the system, then we call it as Q out. Then we take the heat exchange to be negative. So heat given to the system, we call it as heat given to the system also. Heat is given to the system. And this we can take call it as, so this is heat given to the system is positive, heat taken out from the system. See, thermodynamics is a very easy chapter. The only problem is identifying these words, what does this thing word means, and ultimately sign convention. Now most of you are confused between the sign convention in physics and chemistry. So remember, the sign convention in physics and chemistry are same, only the meaning is changed. So for delta U and Q, the sign for heat, sorry, for sign in chemistry and physics are exactly same. There is no difference between the physics and chemistry when you are using the sign for Q and delta U. So these are the two things which you have calculated. Third thing which we have to calculate is work done. So remember here, I am going to calculate the work done by the system. By the system or gas. Now, here the confusion comes because in physics, whenever question is asking you work done, they are automatically asking you work done by the gas. In case of chemistry, they ask you work done by the surrounding. So we are going to calculate the work done by the system because this is the most logical way to calculate the work done. So suppose you have a gas which is in a piston which was initially in this position. Inside this container, you have a gas. Pressure of the gas is P right now. Due to this pressure on this piston, there will be a force F. This force F, I can write pressure of the gas into cross-sectional area of this piston. So I'm going to assume cross-sectional area of this piston is A. So what the gas will try to do, gas will try to expand and it is going to push the piston. When the gas is trying to push the piston, suppose the piston has moved from the position, this initial position to this position. So this is the final position of the piston. Piston has moved up to this point. This distance I'm going to assume as dx. So what has happened to the gas? Has displaced the piston very slightly. It is a quasi-static process. Remember, I explained what is quasi-static process. So here, the gas has slowly moved the piston from the initial position. This is the initial position of the piston. This is the final position of the piston. So the gas has moved the piston by a small amount dx. In this, the gas is going to do some work. So the very small work done by the gas to push the piston from the initial position to final position, I can write F dx. But I know what is F. So I can write this thing as P A into dx. Now, what is A into dx? Cross-sectional area of the piston is A and this distance is dx. So this thing, sorry, I'll mark with a different color. This thing which you are seeing here, this is only A into dx. But A into dx is nothing but a change in the very small change in the volume. You have a cross-sectional area A. This distance is dx. So it looks like a cylinder. What is the very small volume of the cylinder? Volume of the cylinder is A dx. So this is nothing but very small volume increase in the gas. So I can write work done. Very small work done by the gas is nothing but P into dV. I am not interested in very small work done because it has no meaning. I want to find out the total work done by the gas. So total work done by the gas is nothing but integration P dV. Here variable of the integration is V. So I will write V initial to V final. So the work done by a gas for any thermodynamic process, I can write W. W is equals to integration P dV from V initial to V final. This is the formula for work done by the gas. Irrespective of the thermodynamic process, we are going to do this thing. But remember, in the exam, you don't have time to do this integration and all those things. So we are going to write the equation of a generalized process, which we have already done. For that generalized process, we are going to calculate what is the work done by the gas. And we are going to use that formula in different processes. So work done by a gas, I can write close integration P dV from V initial to V final. Here also we have to come up with the sign convention for the work. So remember here I am writing the sign convention for work done by the system, which means I am interested in work done by the gas. In physics, you want to find out what is the work done by the gas. In chemistry, you want to find out what is the work done by the surrounding. So here we are writing the sign convention for work done by the system. The important point is it is work done by the system. Now, what is the work done by the system? If the volume of the gas is increasing, which means the piston is moving in this direction, volume of the gas is increasing, force is in this direction, displacement is also in this direction. So if force and displacement are parallel to each other, work done is positive. So I can say if gas expands, expanding means final volume of the gas is more than initial volume of the gas. Then I say work done by the gas is positive. If work done by the gas is positive, work done by the surrounding will be exactly opposite of this one. So I can say work done by surrounding is negative, which I'm not going to write it because later you will get confused. So just remember, when I say work done in physics, I means work done by gas. So if gas is expanding, work done by gas will be positive. And if gas is compressed, if gas is compressed, then final volume of the gas will be less than initial volume. Then I say work done by the gas is negative. Now remember, irrespective of the subject which you are studying, whether it is chemistry or physics, if gas is expanding, work done by the gas will be positive. If gas is compressed, work done by the gas will be negative. In chemistry, you calculate the work done by surrounding. So when you say in chemistry, you say that if gas is expanding, work done by surrounding is negative. So, and when we are using the chemistry and physics, in physics, we say work done. So if I say work done in physics, then I will read, if gas is expanding, work done will be positive. If gas is compressed, work done will be negative. This is in the physics. In chemistry, it will be, if gas is expands, work done will be negative. And if gas is compressed, work done will be positive. Because in the chemistry, you are calculating the work done by surrounding. So keep this thing in the mind. So this is the generalized formula for work done. But this formula doesn't help me much. So what we are going to do, we are going to find out what is the work done for a generalized process in thermodynamics. So we will write the work done in a thermodynamic process. Again, remember what I am doing. I am calculating the work done by the gas. Work done by the gas, sorry, work done by the system in a thermodynamic process. This TP means thermodynamic process. I can write the generalized equation of a thermodynamic system as PV power X is equals to some constant. That constant I can take anything. So I think I have used the C already. So I'll use the constant as K. So this we have done that for any thermodynamic process, the process equation can be written as PV power X. PV power X is equals to some constant. That constant right now I'm taking as K. From this, I can write P1 V1 power X is equals to K, because it will be valid for each and every pressure and volume. And I can write this thing as P2 V2 power X. So I'm going to use this thing instead of K. I'm going to write this. Now, from this, I can write P as K divided by V power X. K is, remember, a constant. It is not Boltzmann constant or anything. I have taken it as a general constant because I have already used C for specific heat capacity and those other letters are not available. So I used K as a constant. Now, if P is equals to K divided by Vx, what will be the work done by the gas? Work done by the gas will be from V initial to V final P dV. Instead of P, I can replace this value of P in this equation here. So what will I write? Integration from V initial to V final. K divided by V power X dV. So this is the integration. So here K is a constant. Variable of the integration is V. Here also integration, variable is V. Remember, X is not a variable of the integration. X is also a constant. X is a constant, K is a constant. So remember this thing, variable is only volume. So now I'm going to calculate this integration. So the work done by the gas, I can write integration V initial to V final K divided by Vx dV. V power X can be written as V power minus X. So if I want to do the integration of this thing, what will be the integration of this thing? I will just do plus 1 divided by 1 minus X. So the integration of this whole term will be V power 1 minus X divided by 1 minus X. So I can write this integration as, K times, K is a constant outside of the integration. I can write this thing as V power 1 minus X divided by 1 minus x. Integration from V initial to V final. Remember 1 minus x is also a constant. Now, this term I can further write it as, so this is V power x. So I can write this thing as, sorry, so V final, V initial. So I can write this thing as k V final 1 minus x, or I'll take 1 by x common outside. So this will be k divided by 1 minus x, V final 1 minus x minus V initial 1 minus x. Again, derivation not such important because again and again we don't have to do this thing. That's why I'm doing the derivation in one go. Derivation is not important. Final result which comes, it will be important. Now, from here, I can write this thing as k into V final divided by V final power x. I'm going to multiply V k inside. Then it will be k V initial upon V initial x. Remember V power 1 minus x. I'll write it here. V power 1 minus x, I can write it as V divided by V power x. So that is what I have done. So I can write this term as 1 by x, 1 upon 1 minus x. Inside this bracket, I can write this thing as k V final divided by V final power x minus k V initial divided by V initial power x. Now from here, I can write k divided by V final. So if you see here, this k, P is equals to k divided by Vx. So if I write V final, this will be P final. If I write V initial, it will be V initial. So I can write this term as k divided by V final power x can be written as P final. K divided by V power initial can be written as P initial. So I can write this thing as 1 upon 1 minus x P final V final minus P initial V initial. In simpler word, I'm going to write the work done now. I hope you have noted this thing down. I'm going to move on to the next slide. So final work done will be P final V final minus P initial V initial divided by 1 minus x. This term P initial, P final, V final, I can write nRT final. So I can write this thing as nRT final. Then I can write P initial, V initial as nRT initial. So it will be what? T final minus T initial divided by 1 minus 1 minus x. So in general, the work done by a gas for any thermodynamic process, I can write P final V final minus P initial V initial divided by 1 minus x. Or I can write this thing in terms of temperature also, which is nR T final minus T initial divided by 1 minus x. The only thing where it is not valid is where x is equals to 1. X should not be 1. Except this, for any thermodynamic process, I can apply this formula. Because if I put x is equals to 1 here, then it will be nR T final minus T initial divided by 0, which turns out to be infinity. Work done by a gas cannot be suddenly infinity. So, which is not acceptable. So x is equals to not x is equals to 1 is not acceptable. For that, we have to calculate the work done separately. We will see what is x is equals to 1 processes and we will calculate the work done for this. So for x is equals to 1 only, I have to calculate the work done. Except that for all other processes, I can write the work done formula as this. And remember, this is the work done by the gas. So we have covered the three important things. One is what is the change in the internal energy of the gas, then what is the heat, then heat exchange by the system, and then we have done work done. So quickly I will summarize what is the sign convention for these three: delta U, Q, and work done by the gas. Temperature increases, delta U positive. Temperature decreases, delta U negative. Heat in we take as a positive. Heat out we take as negative. Work done by the gas, if it is expands, then W is positive. So the work done by the gas is positive. And if gas is compressed, then work done by the gas is negative. This is for physics. In chemistry, delta U and Q are exactly same as physics. Only you calculate the work done by surrounding. If gas expands, then work done by surrounding will be negative. If gas is compressed, work done by surrounding will be positive. So remember this thing. In chemistry, work done means this. In physics, work done means this. This is the only confusion most of the students have. If you can overcome this confusion, then physics and chemistry, it's like a combined one chapter. You have to study a lot less. But if you don't understand this thing, then you keep on getting confused that in physics this was the formula, in chemistry this was the formula. And first law of the thermodynamics also seems a different, that in physics it is different, in chemistry it is different. It is not. Remember, mathematically both of them are exactly equal, but what you are writing is slightly different. The meaning of the word W is going to be different. That's why you see the difference between the first law of thermodynamics is different in chemistry and first law of thermodynamics is different in physics. At the core of this thing, concept is same. Only mathematical form in which you are writing is different because we are using different symbol. So remember this thing, work done by the gas is nothing but minus of work done by surrounding. This is in physics, this is in chemistry. So if work done by the gas is positive, work done by surrounding will be negative. If work done by the gas is negative, work done by surrounding will be positive. So my advice will be remember physics because it is most logical thing. Gas expands, work done positive, gas compressed, work done negative. Very simple to remember. And remaining delta U and Q are very logical. So I think I have like very less time. So we'll continue in the next class and we will calculate what is the bulk modulus and slope of the PV diagram. And we will calculate what is the specific heat capacity also for any thermodynamic process. So if you have any doubt, you can just message me, and otherwise the class is over now.